Hello everyone, and welcome back to the series on single variable calculus. Today we're going to be talking about a very important topic that makes integration of functions actually quite difficult, especially if you are new to the world of calculus. And that comes down to the existence, or lack thereof, of what we call elementary primitives. So what is an elementary primitive? So the elementary primitive of a function is just the antiderivative of that function, provided that it can be represented as a finite, emphasis on finite, number of function operations, addition, subtraction, multiplication, division, and compositions of functions that are constant, algebraic, such as polynomials, exponential, logarithmic, and trigonometric. Also keep in mind that the hyperbolic trigonometric functions are in this list as well, because they can be represented as exponentials, and technically speaking you can represent trigonometrics as exponentials as well. So pretty much what elementary primitives comes down to is just the awareness of functions, and some people, at least at the basic level, are only familiar with these classes of functions. So it doesn't mean that there does not exist other special functions that can represent them, but it's just that those special functions cannot be represented in terms of these more familiar ones. Let's take a couple basic examples just so that you know what I'm talking about. So suppose we're interested in the antiderivative of 1 over x dx. Most of you already know that this is just the natural log of the absolute value of x plus c. But if you aren't aware of logarithmic functions, then you will not know what the elementary antiderivative or elementary primitive of this function 1 over x is, even though it's very simple to look at. Now, of course, let's make this integral a little bit more complicated. Let's assume that somebody asks you find the integral of x squared minus 5x minus 2 all over x squared plus x plus 1. Yes, it's a little bit more complex, but nonetheless it is a rational function. So if you know logarithmic functions and maybe partial fraction decomposition or long division, you might be able to deal with this integral. In fact, a fun little exercise that I do recommend you basic calculus students is to show that this is equal to x minus 3 times the natural log of x squared plus x plus 1 plus some arbitrary constant c. And there are a couple other ways of representing this as well. So of course that looks complicated, but it can be represented in terms of a polynomial, a logarithm, and a logarithm composed with a quadratic polynomial, right? So it definitely has an elementary antiderivative. But looking at that function blindly and saying, oh, does it have one? Some people can't, immediately see that it does exist. Now let's take another very simple looking function, the integral of dx divided by 1 plus x squared, the quantity squared. Actually looks quite simple, simpler than the one before it. But actually this is equal to, actually fun exercise, x divided by 2x squared plus 2, and then plus 1/2 times the inverse tangent of x plus c. Now for you fancy integral people, I leave that as an exercise for you. That is definitely fun. And another one, suppose that we have the integral of sine of x times the differential of x divided by sine of x plus 1. So this is a fun integral. This is, if you're familiar with the Brescher substitution, this can easily be solved via that, and a few other variations can also be applied to this as well. And one way you could represent this antiderivative is x minus the sine of x over 2. So some half-angle identities, and then on the bottom we're going to have sine of x over 2 plus cosine of x over 2 plus c. This is one way to represent this. Fun and very exciting integral, but again, I leave that as an exercise for you. But nonetheless, the main point, regardless of the ability for you to get these answers, is that they can be represented in terms of functions that are very basic: sine, cosine, inverse tangent, logarithms, exponential functions, and combinations thereof. But now the question is, if I were to choose any basic functions that we know here and take the integral of it, can it always be represented in terms of functions that we know? So let's take this example, the integral of sine of x over x dx. Sine is very easy, 1 over x is very easy, and the multiplication of them is sine x over x. So the question is, does this have an answer in terms of sine, cosine, tangent, exponentials, logarithms, polynomials, combinations of them, finite at least, that can be represented for the integral of sine x over x in terms of those functions? The answer is actually no, right? So no elementary, what we call primitive, exists for this particular antiderivative, right? So that's actually quite sad because it actually looks very easy. Now, again, it depends and comes down to what is your definition of elementary primitive. Is it a constant, algebraic, exponential, logarithmic, trigonometric, or combinations thereof of these things? If that is your set of elementary functions, then no, sine x over x's antiderivative cannot be represented in terms of them. But, how do you know exactly ahead of time? Because some people might look at this integral and try many ways and give up, and then blame that their integral skills are not strong enough to find that answer. But there is a theorem in differential equations that pretty much states that if you can solve, let's say, some special ordinary differential equation and represent its solution nicely, an elementary primitive does exist. Now, I'm not going to go through the very details of what this theorem actually says in the differential equation that it's trying to solve. It's definitely more advanced that I want to get into for a single variable calculus explanation. But do know that in the realm of differential equations, there does exist formal ways of finding whether or not a function has an elementary primitive. So using this special theorem from differential equations, then one can say, okay, the function f of x equals sine of x over x does not have an elementary primitive, right? So that fancy theorem that I'm not stating pretty much justifies this. And what most people do, especially in the beginning, is sort of memorize a list of functions that are super common that do not have elementary primitives, right? So what do we exactly do in the case that you do not have elementary primitives? Because, if we have the integral of sine x over x, which actually looks very friendly, you're like, well, what if I want to solve it? What if I want to analyze it? What if this comes up in very important applications and I want to sort of, generalize it? So what we do is we create new functions that sort of can be added to our list of elementaries in the future. So this function actually has a name. It's called Si of x. So what we usually do, since it's a function of x, we usually create a dummy variable, let's say t, and then integrate that function on some interval that gives us this function having nice properties. So this is called the sine integral. The sine integral. That's what SI in its notation stands for. So what do we gain from creating this function? Well, I can start to ask you very simple questions. What is the derivative of the sine integral? Well, that's just going to be equal to the derivative of this integral defined function, the integral from 0 to x, of sine of t over t dt. And from the fundamental theorem of calculus, we have a lower bound of a constant and an upper bound of x. That's just going to be equal to the integrand evaluated x. So the derivative of Six is equal to psi of x. So what if somebody says, okay, well, what is the antiderivative of sine x over x? Well, you already know that it doesn't have an elementary primitive, but we have a new function called Si of x, and it could be shifted by some constant, that can now represent this previously undefinable function in terms of this now definable function once we have introduced this newly created function, psi x. Now, a couple little analytical properties about this function, psi x, that is notable to mention. So it actually has two horizontal asymptotes. And depending on how you define horizontal asymptotes, some people define them as, approaches but never touches. These asymptotes, they do approach, so some people will call these asymptotics of the function. So pretty much what this function looks like is on the left-hand side, it sort of goes up and below and up and below and up and below, and pretty much converges to a constant function to that asymptote, and this one goes below, above, and sort of wiggles and converges to that function. And these horizontal asymptotes do have values. The top is y is equal to pi over 2, and the bottom is y is equal to minus pi over 2. So plus or minus pi over 2 are horizontal asymptotics for this function. So if you take as axiom this particular graph and those particular properties, we have the limit as x approaches infinity of psi of x is equal to pi over 2. And we also have that the limit as x approaches minus infinity of psi of x is equal to minus pi over 2. So there's some nice properties about the sine integral function. But is there anything else that we can get from these limit properties? Actually, yes. So let's write this integral, or this limit, the limit as x approaches infinity of psi of x, as an integral. Well, by definition, psi of x is the integral from 0 to x of sine of t over t dt. So we can just replace x with that upper boundary of infinity, so we can write this as the integral from 0 to infinity of sine of t over t dt. And this is actually a very famous integral that people love solving. Some people will say it's one of their favorite integrals to solve. But we already know the limit as x approaches infinity of psi of x is pi over 2. So that means this integral is also equal to pi over 2 as well. So this is just a special integral, I guess you could say, and a special value of that special integral that you can know as long as you know some properties about sine integral function. But of course there's a couple other fancy ways, I guess you could say, of solving this integral, but I won't get into the details of that. So we have this sine integral function. So we have the sine integral function, which is the integral from 0 to x of the sine of t over t dt. And we have a couple other integrals that I want to mention. There's a cosine integral function, but I don't want to bring that character up now. But we have this function, shi of x. So this is called the hyperbolic sine integral. So this is the integral from 0 to x of the hyperbolic sine of t over t dt. And these actually have a very interesting connection. So if you do the sine integral evaluated at ix, where I is the square root of minus 1, you can actually show that this is equal to I times the hyperbolic sine integral of x. So these two special integral functions are actually connected in a very interesting way. And then we have the hyperbolic cosine integral of x, which some people will define as minus integral from x to infinity of the hyperbolic cosine of t over t dt. And yeah, again, there is a cosine integral, but I don't want to bring that up right now. And there is another way of representing this function, but I'll bring that character up a little bit later. Now, what do we get from introducing these functions? Well, I can ask you some basic questions. So what is the derivative of the hyperbolic cosine integral function? And you're going to be like, oh, well, that's just the derivative of the negative integral from x to infinity of hyperbolic cosine of t over t dt. And you can be like, oh, that negative will flip those bounds, so I can actually write that as the derivative from infinity to x of hyperbolic cosine of t over t dt. That bottom can be taken as a limit and then viewed as a constant. So then we can just apply a fundamental theorem of calculus here, and that would just be the hyperbolic cosine function divided by x, right? So that's the derivative of chi of x, and obviously that's going to be true. And one could ask, okay, what is the antiderivative of the hyperbolic sine of x divided by x dx? And you're like, oh, well, it doesn't have an elementary primitive, but I do know a special function called the hyperbolic sine integral of x plus some arbitrary constant c, and now we can define it quite easily. So there's some basic functions that you definitely should know, and they do come up in a few different locations. So now that we've introduced three new functions that one could potentially define in terms of their set of functions that I know and can use, in particular the sine integral, hyperbolic sine integral, and the hyperbolic cosine integral, now I just want to mention a few more other integrals that do have several applications, especially in the realm of physics, engineering, ecology, and biology. So the first family of integrals that I want to discuss is known as the Fresnel integrals. Fresnel integrals. And the Fresnel integrals usually come in a pair. The first is called the Fresnel sine integral, so the Fresnel sine integral, and that's defined as the integral from 0 to x of the sine of t squared dt. So you know you can integrate sine of t, but the sine of t squared is actually non-elementary. So this integral, although it looks very friendly, actually doesn't have a nice answer, so we define a new function called the Fresnel integral function, or the Fresnel sine integral function, which looks at the integral from 0 to x of sine of t squared. And its counterpart, which I'm going to denote by CF of x, so SF is the Fresnel sine, so you can probably guess what CF stands for. That's going to be the Fresnel cosine integral, and that's going to be equal to the integral from 0 to x of the cosine of t squared dt. So you have these two functions that are actually pretty nice. And you're like, okay, well, what can I do with that? Well, I can say, okay, well, what is the derivative of the Fresnel sine integral of x? And you can be like, oh, that's just going to be the sine of x squared. And I can be like, okay, well, what's the antiderivative of the cosine of x squared dx? And you can be like, oh, that's just the Fresnel cosine integral of x plus c. Right, so then you can answer questions of that simplistic nature. A couple little graphical properties about the Fresnel sine and the Fresnel cosine integral is that they both do have, similar to the sine integral, a horizontal asymptotic. So the horizontal asymptotic is up here. So one of these functions is going to go up and sort of converge to there. And the other function, and I'm not going to tell you which one, is going to go up here and then sort of converge as well. So one could ask, okay, if they both have horizontal asymptotics of the same value, is there something special about this number, and does this number have a well-represented value in terms of numbers that we know? And the answer is actually yes. Now, this exercise is, I don't know, I guess slightly difficult. It depends on what skills you know. But it says the following. So the limit as x approaches infinity of the Fresnel sine of x is equal to the limit as x approaches infinity of the Fresnel cosine of x. And both of them are actually equal to the square root of 2 pi divided by 8. So the square root of 2 pi over 8. So this is actually a very interesting looking number. But that's what this little horizontal asymptote is equal to. So that's actually pretty fun. So from this limiting value, then we immediately get a couple improper integrals as results. So in particular, the integral from 0 to infinity of the sine of x squared dx will be equal to the integral from 0 to infinity of the cosine of x squared dx, and both of them will be equal to the square root of 2 pi divided by 8. So we get those two things as immediate results. Now, another generalization, I guess you could say, or closely related family of the Fresnel integrals, and also the sine and cosine integrals, are what is referred to as the Böhmer integrals. So the Böhmer integrals. And the Böhmer integrals are defined as follows. So they're actually parametric defined functions. So we have SB, so B for Böhmer, and then x alpha, alpha parameter. And this is defined as the integral from x to infinity of t to the alpha minus 1 times the sine of t dt. And then we have its closely related cousin, cb of t, so this is the Böhmer cosine integral. So that's going to be x alpha, and this, take a guess of what this is defined to be. X to infinity of t alpha minus 1 times the cosine of t dt. So this is the Böhmer integrals. Very, very nice. Now, I leave as an exercise for you to explore. So question, can you find the relationship? Because notice we have a cosine t sine t and a t to some power for which we can control alpha to SF, CF, CB, and SB. So is there a connection between these Böhmer and Fresnel integrals? And also let's throw in the other characters, for example, SI and maybe even CI, if you want to sort of look that up and see what the connection is between all of these six. So I think those will be good exercises to explore on your own. Another very similar or simple looking integral that you may think has an elementary primitive, but it actually doesn't, is known as the exponential integral and is commonly denoted by capital EI of x. And it's defined as the integral from minus infinity to x of e to the t over t dt. So it sort of follows the same exact notational constructs as the sine integral and also potentially the cosine integral, sine x over x and maybe cosine of x over x, but actually it's cosine of x minus x over x. But it has this function over just x, right? So this actually doesn't have an elementary primitive, and hence its definition. So if I say, what is the integral of e to the x over x dx, you're going to be like, oh, that's just the exponential integral plus c. And I could ask you, okay, what's the derivative of, I don't know, ei of x squared? What's that? Well, if it starts combining functions with other functions, well, you know how to deal with that. So you can use the chain rule. So that's going to be equal to e to the x squared over x squared, and then we can multiply by the derivative of the inside, which is going to be 2x, and then we can simplify that if we really need to. So that's the exponential integral. So no, not only trig functions have special representations, exponential functions definitely have some famous characters as well, and logarithms, but we'll get into them another day. But there's one function that actually has a lot of applications, which some of you might already be aware of, and that is the error function. So the error function, so it's not named after a function, or apparently it is, but it's not like sine, cosine, exponential, logarithm, polynomial type of thing. So what is this? So this is abbreviated by ERF for error function, and it's lowercase letter e. And this is defined to be equal to 2 divided by the square root of pi times the integral from 0 to x of e to the minus t squared dt. You might be thinking, well, that's a strange looking integral. And you might be right. So a couple graphical properties that you might be able to construct from this particular integral. It's actually going to look like this. It's going to look like this. Horizontal asymptotes are not super hard to get. Y equals 1 for the top and y equals minus 1 for the bottom. So those are truly horizontal asymptotes. They approach but never cross. So we can see, at least from the graphical side, that ERF of positive infinity, or the limit thereof as x goes to infinity of ERF of x, this is going to be equal to 2 over the square root of pi times the integral from 0 to infinity of e to the minus t squared dt. From the graphical analysis, that's just going to be equal to 1 because that's what it approaches as x goes to infinity. So what can we get from this particular statement? Well, we can actually solve for the integral underneath the, aside from the 2 over square root of pi. So we can see immediately that the integral from 0 to infinity of e to the minus x squared, if we just do a change of variables, this is actually equal to just the square root of pi over 2. So what's so special about the integral from 0 to infinity of e to the minus x squared? Well, e to the minus x squared, this function here, y equals e to the minus x squared, is actually an even function. It's symmetric about x equals 0. So if this area right here is the square root of pi over 2, that means this area right here also is equal to the square root of pi over 2. So that means from symmetry, we can immediately get that the integral from minus infinity to infinity of e to the minus x squared dx is just equal to the square root of pi. Now, there are other fancy ways you could get this answer. Using polar integration is probably one of the more famous ways, aside from using graphical techniques and other limit geometry tricks. But this is definitely very, very, very famous, probably one of the more famous integrals that people do in lower to mid-level calculus explorations. Right? So if I take a look at this particular function and I define a function, let's call it fx of x, to be equal to 1 over the square root of pi times e to the minus x squared, where x is a real number. So what's so special about this function? Well, if I look at its graph, it has this bell-shaped looking curve, and by construction, the area underneath this curve is equal to 1, and it's always positive. So that means this is a probability density function for some continuous random variable x, right? So if you watch my video on continuous probability theory, or you have done some statistics or probability, you probably recognize this shape as the bell curve, but this is actually not the normal distribution. The normal distribution is actually more commonly defined as fx of x is equal to 1 over the square root of 2 pi, and oh, there's the square root of 2 pi, or the 2 again, e to the minus 1/2 x squared, where x belongs to the set of reals. Now, there's some special statistics reasons why one would define it to be this way, but this, again, will still have the area underneath this curve to be equal to 1. But this is called the standard normal probability density function. And it is defined to be centered around 0, and pretty much all of the data underneath this curve, about 99.7%, is in between -3 and 3. So if this is truly a standard normal PDF, I suggest you justify to yourself, at least mathematically, that the integral from minus infinity to infinity of 1 over the square root of 2 pi e to the minus 1/2 x squared dx is truly equal to 1. Now, if you want to practice your u substitution in addition to these things, let's assume that mu is a real number and sigma is a positive real number as well. So, what if I ask you, what is the integral from minus infinity to infinity of 1 over sigma, square root of 2 pi, e to the minus 1/2 x minus mu over sigma, the quantity squared, dx. So what if I ask you, what do you think this area is equal to? And you probably can guess this is actually equal to 1. The only difference between this and the other, this is actually called the general normal probability density function, where mu is sometimes referred to as the mean of the distribution, and approximately, if you go 3 sigmas to the left and 3 sigmas to the right, sigma is sometimes referred to as the standard deviation of the distribution, you're going to get something, this area, approximately 0.997, but if you go from minus infinity to infinity, you will get 1. So the normal probability density function is truly a probability density function. So those are just some special functions, exponential integrals, sine integrals, Fresnel, Bomer, and a few other honorable mentions. There are infinitely many potentially other special functions that are definitely important, so if I'm leaving them out, it doesn't mean that they're not useful, but we're definitely going to get into a discussion of several special functions in another series. So I hope you enjoyed this little exposition, and I hope to see you in the next one. Take care.